Okay, this lecture is going to go over hypothesis testing goodness of fit unequal proportions for the final project. So I'm going to go ahead and share my screen. And we've got this right here, the unequal proportions. We've got the same thing as the equal proportions. If you want to see more information on the cars for the equal proportions, essentially what we have here, let's read through this. This data allows you to compare the proportionate frequencies of numbers of cars in the independent category car classes in random samples of, it's actually 112 cars, random samples of 112 cars compared to the desired frequencies of the independent category car classes in the desired proportion of car classes. And so we have the desired proportion of car classes, which is right here, and the actual number of cars in each class right here. So we have a total of 112 cars, and of those 112 cars, they are split up between 5 different classes: Class A, Class B, Class C, Class D, Class S. And depending on the class that they're in, they can race in different classes, or they can race in different races. And so you want a certain number of cars in class A, certain number of cars in class B, class C, class D, class S. S is the special. D, I really don't know what these stand for. They're just different letters. But say, for instance, that they want the cars to be in particular classes to make sure that only certain cars could race in certain races. So for us, we want it to just be 0.1. We only want 10% of cars to be labeled as special. And we want A to be the most common, B to be the second most common, C to be the third, D to be the fourth, and notice how it goes in order 30% down to 10%, how we only want cars in those classes. Okay, so Hot Wheels has a total of 5 different classes of cars designated by letter. A random sample of 112 cars was taken to determine if cars within each car class reflect the desired proportion of 0.3, 0.25, 0.2, 0.15, and 0.1, as some classes are supposed to be more rare than others. I can only have a 5% chance of type 1 error. So just like with the goodness of fit with equal proportions, it has the same dependent variable, right? What we're actually examining is the frequency of the number of cars in each class. So we've got the frequency of cars, okay, and then the independent variable is the car class. So the frequency of the number of cars is dependent on the class that they're in. So we've got these 5 classes right here. And then we've got the number of cars in each class. So we've got the dependent variable and the independent variable. And then what type of data is the independent variable? And that's going to be categorical or nominal, because they're just categories. We've got these 5 categories are nominal because there's really no particular order, although you could kind of say, oh, we want them to be in order from, least rare to rarest. We're still going to call them nominal, because that just opens up a whole nother can of worms, calling them ordinal. And so we are going to look at, what are you examining or comparing? Sorry. And so what we're going to do is we're going to look right here for goodness of fit for unequal. And remember, you can look right in here, and these are color coded, so you can be like, oh, what are we examining or comparing? Later you're going to look at the null and alternative, the assumptions, the effect sizes, and what you can look at is right there. But what are we comparing? So look at these 4. Are we comparing the observed frequencies and categories to those frequencies that would be expected from a hypothesized distribution, aka normal, to determine if the observed frequencies differ from a known or hypothesized distribution, to use this test to compare observed frequencies, frequency distribution to an expected frequency. In other words, like we expect these frequencies from the year 2000 to match the frequencies of year 2001. That's what that's saying. To determine what categories or classes are different, contribute to the most overall difference in the categories or classes. But we're going to stick with this one right here to determine if observed frequencies differ from a known or hypothesized distribution or population. So and the reason why is we have these desired frequencies or the hypothesized frequencies. And so we copied and pasted this. So if you, hold on. Yeah, this is what you want. Use this test to compare the observed frequencies. So I'm going to copy and paste this one, Control C, and I'm going to come right in here, and I'm going to compare, let's see here, to compare the observed frequencies of cars in 5 different classes to the expected frequency distribution um, in which the expected frequency uh, matches the desired rarity or uh, proportion rarity. Let's do rarity of cars. Okay. In other words, Hot Wheels wants it to be wants it to have a certain rarity. Okay. Okay. So here we go. We've got goodness of fit for unequal proportions is the test that we're conducting, and it is a right tail test because all of these are right tail tests for what we're doing. And let's just go through the decision tree really quick to show you why it's a right tail test. You can either look at continuous data from a sample or a population or frequencies of categorical data. So we have 5 different categories and we are looking at the frequencies in each of those 5 categories. So that's what we're doing. We're looking at the frequencies. So I'm comparing the observed frequencies to an expected frequency distribution, which are the group frequencies expected to be equal? And the answer is no, they're expected to be unequal. So we're going to do goodness of fit chi-squared for unequal proportions, which is these right here. And so you can follow these right here, or we're just going to do it right here. So like I said, we have the desired frequencies, which if you wanted to, the desired frequencies, I have it listed as, 0.3, 25%, 20%, 15%. You could do, these are the proportions. They're already the relative frequency, or you could look at it as 300, 250, 200, 150, and 100. And it's the exact same thing. Right, it's I just had it as the proportions. Somewhere I messed it up there. 300. Oh, I see what I did. um this should be 250. There we go. 200. So this is what it would look like if you actually had real frequencies, but because we're dealing with we already say, oh, we want it to match up with these proportions, we actually just put the relative frequencies in there already. So what we did from here is I'm going to delete this and I'm going to say, okay, I have these relative frequencies, and the way that I got the relative frequency is I did equals this desired frequency divided by the total, and then I did the dollar sign. So this desired frequency divided by the total, and then I just dragged it down. And what that did for me is it gave me the relative frequency, which is in this case the exact same thing as the desired frequency. Okay. Next, multiply the relative frequency by the total in the category 1. So we're going to do equals, multiply this relative frequency multiplied by the total number of cars in category 1. So we're going to bring that right over here. Okay. And we're going to put the dollar sign. And we're going to drag it down. Okay. And this gives us, based on this total number of cars, this is what the expected frequency should be. this is what the expected frequency should be. And I'm going to change these borders really quick because there we go. So this is what the expected frequency should be based on the number of cars that they have and the desired frequency. So that's how you calculate the expected frequency. And this is really the only difference between goodness of fit for equal proportions and unequal proportions. Instead of having it equal all the way down, you're saying this is what I want it to match, which is unequal. So I'm going to copy this and make sure that these match up, you know, A, B, C, D, A, B, C, D, S, A, B, C, D, S, and I'm going to bring it right down here, and I'm going to paste the values. Make sure that you paste the values because I've got formulas in there right now. And if you paste just the formulas, you'll notice, it messes things up, or it could give you all sorts of things that are just off. And then same thing, Control C and paste just the values. And then I already actually have these in there, A, B, C, D, S. Okay. And then what I'm going to do is I'll come back to this in just a minute and actually do all of the calculations in here. But let's come back over here. And we already determined the type of test. And now I'm going to say, what is the null and alternative hypothesis? The null hypothesis is there is no difference in the frequency of classes of cars between the 5 classes and the desired proportion of car classes. So in other words, there is no difference between this relative frequency and this relative frequency. Okay, there is no difference between these two. Okay, that's what this is saying. Let's see if we can write this a little bit clearer. Let's see. There is no difference in the frequency in the observed frequency of classes of cars and between the 5 class. Let's just do and the desired frequencies of car classes based on the desired proportions from hot. Okay, there is no difference. So, and then it makes it really easy. You can literally just copy and paste this. Control C, Control V. There is a difference in the observed frequencies of classes of cars and the desired frequencies of car classes based on the desired proportion of Hot Wheels, which it's kind of funny. This really isn't telling us a whole lot of information. It's just saying there is no difference or there is a difference. And so that's why a little bit later we're going to go into interpreting the difference and how we can go from there. Next, what is the level of significance? It's 0.05 based on I only have a 5% chance of type 1 error. Test statistic is chi-squared. What are the degrees of freedom? It's the number of classes minus 1. So there are 5 classes. So the degrees of freedom is 4. And then the critical value. The way that you calculate the critical value is we're going to use this formula chi-squared dot inverse dot right tail because we're doing a right tail test. It is possible to do a left tail test with chi-squared. It's just we are not doing a right tail test with chi-squared, or sorry, a left tail test. So you can technically do a left tail test. We're just not doing one. So everything in this class is going to be a right tail test, and you'll notice we've got a 5% chance. And so for this particular instance, the region of rejection is above a 16.9 or greater than a 16.9. But for ours, what we're going to do is with a 0.05 and a degrees of freedom, so an alpha of 0.05, degrees of freedom of 4, our region of rejection is anything above 9.48. So this right here should say 9.487. So anything above 9.487 or more extreme than 9.487, we're going to reject the null hypothesis. Okay. And so now let's take a look at the assumptions. So we're going to look right here, and we've got assumption 1, 2, 3, and 4. So one categorical variable, and we do have one categorical variable. The categorical variable is the car classes, and it's split up between 5 categories. And then independence of observation. So with independence of observation, what we have here is every single one of these cars is a different observation. And they are a different observation. And I'll show you. We have the cars. They are right here. I actually did the test. So each one of these cars is a different observation. I've got more cars on the other side. So we tested all of these cars, and they're a different observation. Um, and yeah, so we have all these different observations, and so we have independence of observation. Next, there must be an expected frequency of at least 5 in each group. So let's look at this. So the expected frequency, we've got 33.6, and it's got to be greater than 5. 28, 22.4, 16.8, and 11.2. So this is the one that's the closest to 5, but it's definitely still above 5. So we are good to go there. Next, the assumption 4, the expected frequencies for all categories are reflective of unequal proportions. In other words, they're reflective of something else, and these all have to be unequal. So this is unequal. So we are good to go. There are no violations of assumptions, so we can keep on going with our test. If there was a violation of assumption, we should really look at possibly conducting a different test. Next, we've got calculate the values. So we're going to calculate these values, and let's do it from here. And I'm going to, there we go. So we've got, let's just follow this. Frequency observed minus frequency expected. So we do equals frequency observed minus, whoops, frequency observed minus frequency expected. Okay, so this is the observed is 18 below what's expected, and we're just going to drag this down. The observed is 2 below what's expected. The observed is not below at all what's expected, but the problem is, once again, we need to give some decimal points. So we've got some decimal points there. So it is 0.4 below what's expected, 4.2 above what's expected, and 15.8 above what's expected. Okay, so the next thing that we've got to do is equals this value right here squared, frequency observed minus frequency expected squared. Okay, and then we're going to drag it all the way down. And then we are going to do equals frequency observed minus frequency expected divided by frequency expected. And this right here is the contribution to chi-squared. Okay. So we've got the individual contribution to chi-squared. And then this right here is, we'll get to that in just a minute. So we've got all these different values right here, the individual contribution to chi-squared, and we are going to equals sum. We're going to add all these up. Oh, another thing that I forgot to mention, you need to make sure that the values in here equals sum. The values in the observed frequencies match the values in the expected frequencies. And if they don't match, you've got to figure out what you did wrong to make sure that they do match. So it's 112 and 112, observed matches expected, and you're good to go there. So next, we've got chi-squared, these values right here, which gives us a total chi-squared value of 32.708. So coming back to this right here, remember this was supposed to be like 9, anything greater than 9 or more extreme than 9, we were going to reject. Well, it's all the way over here at 32. So with this chi-squared distribution, we can definitely know that it is more extreme than chi-squared. More specifically, the probability of randomly getting this, assuming that there is no difference between the two of these, between observed and expected, is less than 0.000001. So a very low probability of this occurring. So let's come back over here, and we're going to say, okay, calculate what is the calculated value of the test statistic, and I'm just going to do equals. And I'm going to put in what is the calculated value? Whoops, G38. So that's a calculated value. And then we're going to do the p-value, or the probability of observing this. And then we're going to do less than 0.001. The probability of getting these results or more extreme, assuming that there is no difference between the observed frequencies of cars and desired frequency, is less than 0.001. Okay, in other words, the probability is very low. Okay, What is your decision? Our decision is going to be reject the null hypothesis. And we're going to say, because the calculated test statistic of 32.71 is more extreme than the critical value of 9.49. We reject the null hypothesis as the results indicate the frequencies of cars in each class do not match the desired frequencies. Okay. In other words, there's something off somewhere. Okay. But now the question is what's off? What is it that's off? What is it that's wrong? And so we need to take a look at it and just do a little bit more diving in to see what is it that is contributing to it being off. Because all that we know, the only thing that we know is that there is something off. There is something off, but we don't know what's off yet. So next, we're going to find what is the percent contribution. So each one of these contributes something to chi-squared, but which one of these contributes the most? Which one contributes the least? What is it that's really off? So the way that we do this is we are going to do equals the individual contribution to chi-squared divided by the total chi-squared value. Okay, and we're going to put a $sign right there. So this gives us the percent contribution to chi-squared. Okay, or the proportionate contribution. Let's do that. Proportionate contribution to chi-squared. Okay, so this contributes 28% to chi-squared. This contributes less than 1%, less than 1%, 3%, and 68%. The only thing that I care about are the ones that are 28% and 68%. Anything that is above 10%. And the reason why is because the margin of error, these right here, basically the margin of error would be greater than the percent that they're off. And I could show you that, but it basically is anything that's less than 10% contribution to chi-squared could be accounted for by margin of error. And so we've got the percent differed from expected. So we've got, so we've already got, yeah, so we've got how much they contributed to chi-squared, and now we've got the percent that they differed from expected. So we're going to do equals the frequency observed minus frequency expected. So this column right here divided by, this column right here divided by the frequency expected. So we're going to do equals frequency observed minus frequency expected divided by frequency expected. So this is 52% below what's expected. And we're going to drag this down. This is 7% below, 1% below. This is 25% above, and this is 141% above what's expected. Okay, once again, we don't care about these. Why? Because these are greater than 10%, or these are not, these are less than 10%, but these are the ones that I care about. Okay, this one is less than what's expected, and something that I like to do just to help me with interpretation is I like to highlight these, like highlight this in sort of like a reddish color if it's below what's expected, and I like to highlight the green one, or the ones that are above what's expected in like a green shade. It's like, oh, this is above what's expected, this is below what's expected. Okay, and so I'm going to come over here and I'm going to say, okay, what is it, Control C, what is it that contributes to chi-squared? Okay, and so we're going to say class A contributes and class S contributes. So I'm going to delete this class C. Okay, class A contributes 28%. So I'm going to change this, 28% of the chi-squared value, and is, see here, 52% lower than what's expected, with a total of, let's see how many cars are in class A, with a total of 16 cars in class A. Okay, so that's what I did. I said there's 16 cars in class A. It's 52% below what's expected. And it contributes 28% to the chi-squared value. Okay, next, class S contributes 68% to the chi-squared value and is 141% greater than what's expected, with a total of 27 cars in class S. Okay, so I'm gonna, okay, so we wrote up, this is where the difference comes from. And that's what we really care about. It's like, yes, there is a difference, but now let's tell us where the difference comes from. And we're going to put that right here, okay, in the explanation section. And then right over here, I'm going to say the two classes that contribute more than 10% to the chi-squared value are class A and class S, because those are the only two and the only two that I care about interpreting. Okay, so next, what is the effect size? In other words, is this observation really even noticeable? Or is the result really even noticeable? So I'm going to come down here and I'm going to calculate the Cramer's V effect size, which is different than what we have been calculating. And so we've been calculating Cohen's D. Now we're calculating Cramer's V. So first of all, we're going to do equals. We're going to put chi-squared value right there. The total number of observations, which is 112. The degrees of freedom, which is 4. And so now we are going to calculate Cramer's V. And so the Cramer's V formula is right here. So we're going to do equals square root and put in parentheses the chi-squared value divided by the put in parentheses numbers multiplied by the number of observations multiplied by the degrees of freedom, and then put those in parentheses as well. Put the denominator in parentheses, and then press enter, which gives you a Cramer's V of 27 or 0.27. And the way that you interpret this, you look at degrees of freedom, and then you find, okay, this is a small, medium, large. So this is 0.27, which means that it is a large effect size. Okay, it's a large effect size. So in other words, even with a small sample size, you can see that there is a difference. So we're going to put, what is the Cramer's V? We're going to do equals right there. So we've got the effect size of 0.27. 0.27 is a large effect size. The results indicate that with a small sample size, it would be possible to observe the difference. Okay. So that is how you calculate all of the information here. So the results basically indicate there is a difference. The difference comes from A and S, classes A and S, and even with a small sample size, you can observe the difference. The next thing that you're going to do is with your group, write all this up. What was run? A chi-squared goodness of fit for unequal proportions was conducted. Comparing what to determine if the observed frequencies of classes matches the desired proportion. Once again, you can literally just you can come up here and say, what was the purpose of the test? Hold on. Did I even have that up here? I should. Oh, yeah. To determine if the observed frequencies, oops. There we go. Come down here and say, to compare and observe frequencies of cars in pair the observed frequencies of cars in 5 different classes to the expected frequency distribution in which the expected frequency matches the desired rarity of cars. Okay. What was the result? The once again, you can just look right here. What was the result, or what was your decision? Because the calculated statistic, we're just going to copy this and put this right here. Because the calculated test statistic of 32.71 is more extreme than the calculated value of 9.49, we reject the null hypothesis, as the results indicate the frequencies of cars in each class do not match the desired frequency. And then what is the p-value, or the probability of getting your results? Once again, you can just copy this, Control C, and just put this right here. Okay, and then give insight. The results appear to be due to class A being lower than expected and class S being much greater than the expected frequency. Okay, and then talk about the chi-squared. you can copy and paste this, Control C, and just, go over this with your group, make sure that you guys are all on the same page with this. And then how should these results be used? The present results can be used to indicate classes do not reflect the desired proportions. The manufacturers should consider not producing as many Class S cars and producing more Class A cars to meet the desired proportionate. Okay. So just telling them, hey, you can use this to do X. Last but not least, you need to make a relative frequency distribution. So we are going to make a relative frequency distribution right here. We're going to just literally highlight this and do insert. And we are going to, you can do it like that, or they're going up. You can do it like that, going to the side. Let's just go ahead and do this right here. Observed frequencies, which is in blue, the desired frequencies or the expected frequencies, which is in orange. And you can put frequencies of cars by class. When I say relative, I really meant a frequency distribution or a frequency chart. So we're going to bring this right down here and drop this right there. And that is how you put this together for the chi-squared goodness of fit for unequal proportions, where the observed frequencies should be are being compared to the expected frequencies, in which the expected frequencies are not equal. Other than that, I think this is pretty straightforward. If you guys have any questions, feel free to send me a message.